So thanks. So my name is JC, so I'm basically Steve's fluid mechanics guy. And Steve asked me to give you a brief overview of SINDy, and I figured that rather doing like a long list of examples of what you can do with SINDy, I'll actually focus on one fluid configuration I'm working on, which is chaotic convection, and now we can get Lorenz-like system from such a high-dimensional system. So in fluid mechanics, where I'm studying like different fluid configurations, so this one's the cylinder fluid that Steve mentioned before, pretty simple flow, really not that interesting actually from my point of view now that we've figured it out. This is another kind of flow I'm interested in. So this is it's rocket science literally because this is a rocket engine nozzle, and you have a turbulent fluid that comes out with shock waves and super complex physics. This is the end goal. This is the kind of application I'm targeting, but this is just out of reach for the moment. So we're going to use this simpler problem today as some kind of illustration of what you can do with SINDy. So this is a thermal exchanger. It's called a thermosiphon, annular thermosiphon. What you can see is the temperature field. And so we heat the lower walls and we cool the upper walls so that we have a temperature gradient. And so we get these convection cells that appears, and we have some kind of fluctuation, and then randomly it will switch from clockwise to anti-clockwise rotations. And that's actually what we're going to study today, and we're going to try to get SINDy model for it. So we're going to make a very simple assumption. We're just going to use 2D flow assumption for our problem in compressible. So that's the Navier-Stokes equations. For the velocity and for the temperature, we have a few parameters. Maybe you're more familiar with the Reynolds number than Rayleigh and Prandtl numbers. But that's basically just physical parameters, not that interesting. If we want to simulate it, we have approximately 50,000 grid points. We have 4 state variables, so the 2 velocity component, the pressure, and the temperature. So that's approximately 200,000 degrees of freedom in our system. Looking at this video, it clearly looks like I don't need 200,000 numbers to characterize the flow. And so we're going to try to get a reducer model for it, primarily for flow control purposes. And so the idea is, if I take the flow rate through this cross-section, that's what it looks like. And so for anyone familiar with Lorentz system, this is precisely what Lorentz time series look like. Was like the dashed line is a 0 flow rate, so we have switching between clockwise and anti-clockwise rotation of the convection cell. And so the idea is that if this suspiciously looked like Lorentz, probably we can have a low-order model to describe these dynamics of interest. So we're going to try different questions, answer 2 different questions. The first one is, what are the physical properties our reducer model should have if it indeed is Lorentz-like dynamics? And for that, we're going to analyze the physics. On the simpler problem, we're actually going to rederive the Lorentz system from Rayleigh-Benard convection just to get some insights on how we should treat our problem if it's indeed similar. Then we're going to look at how we can get low-dimensional embedding for our system, and then how we can use system identification, so SINDy, to get the governing equations of the dynamics in this low-dimensional embedded space. So let's get started with a Lorentz system. So if you didn't know, so I guess most of you are familiar somehow with Lorentz chaotic systems. Maybe you didn't know it actually comes from fluid mechanics. It's the Rayleigh-Benard convection. So that's 2 infinite flat plates. So it's a similar problem than the one we're looking at. It's a bit more like academia than industrial application. But 2 flat plates, the lower one, we heat the fluid. So hotter fluid gets lighter, it goes up, and the upper plate, we cool it. So it goes down, and it has numerous applications in geophysics, oceanography, meteorology, and all that stuff. From a dynamical system point of view, it's pretty interesting because it's a pretty well-known model for nonlinear and chaotic dynamics, pattern formation, and we also use it for fully developed turbulence. So that's the same equations as before, right? Under appropriate non-dimensionalization, we get the Navier-Stokes equations plus the temperature equation. And so once we have these equations, we can ask the question, all right, what's the fixed point of our system? Do we have any equilibrium solution in our problem? And the simplest one is going to be, we're going to have no flow. If we do that, this all set of PDEs, they just reduce to the heat equation with appropriate boundary conditions. That's the temperature profile. That doesn't really matter. And so now we can ask, all right, once we have this, that's exactly what we're doing, like the step-by-step derivation that Lorentz did in 1963. Once we have this solution, we can ask, all right, is it stable or unstable? So we're going to consider the linearized problem. Well, I wrote it slightly differently than before. Psi is basically the stream function, what we call in fluid mechanics the stream function. You should really understand it as the velocity field. It's just a different way to write it. So these are our equations, linearized equations. We can look at their stability, look at the eigenmodes, and all that stuff. So if we look at the eigenmodes, we plug it into our equations here. So we're going to have horizontal wave number, Fourier decomposition in the horizontal direction, and then lambda will control whether our perturbation, our state is stable or unstable. We get this generalized eigenvalue problem. We can solve it analytically. In this case, it has been shown in 1916 that if we use free-slip boundary conditions, that's what our eigenmodes are going to look like, and that's the dispersion relation. So anything in this region are unstable operating conditions. So if I choose a given Rayleigh number, that's basically a given temperature difference and a given horizontal wavelength, like that would be the critical one, and that's the one Lorentz chose to design his reducer model. So that's the instability we have, right? So we have the convection cells, and the contour lines are basically the temperature fluctuation. So we have hot air that rise up, cold air that goes down. And now the question is, how does these evolve non-linearly? So the nonlinear equations are pretty similar to before. That's the linearized equation on the left-hand side, and then we have these nonlinear Jacobian operators that basically are our nonlinear term. We're still going to assume free-slip boundary conditions. And it was shown by Saltzman in 1962 that actually the general solution to this set of equation here, you can actually express it as an infinite Fourier series. That's not very convenient. What Lorentz did was he actually considered truncated Galerkin expansion, where the velocity, the stream function of the velocity field, basically, he only considered a one-mode expansion, where this mode, that's precisely this velocity field. And then for the temperature, he considered two different modes. The first one, whose amplitude is given by B, is precisely this temperature fluctuation. And then another one, which you can understand it as some kind of modification of the mean temperature profile due to the onset of convection. So modification of the linear, like 1 minus y temperature profile due to the fact that we have convection that comes in. And so if we put these into our equations, eventually we end up with a set of 3 ODEs that governs the amplitude of the velocity field, of the temperature fluctuation, and of what we call the mean flow distortion in terms of the Prandtl number, in terms of our physical parameters. And that's precisely Lorentz system. So that's how he derived it. He used one velocity mode and two temperature mode, from a Galerkin expansion, had a lot of knowledge about the equations, and eventually once you have this, you can rescale a bit the parameters, and you end up with the well-known Lorentz system, which everyone knows now that already. It has chaotic dynamics. These are the classical parameters that everybody considers. But the question is, all right, if our system, like our analog thermosiphon, is somehow governed by a similar equation in this low-dimensional space we're looking for, what are the properties our system should have? And so let's quickly look at the property of the Lorentz. So it basically has three important properties. The first one is it's invariant with respect to the transformation x, y, z goes to minus x minus y, z. Right? So if I replace x and y by minus x and minus y, doesn't change my equations. They're invariant. The vertical axis actually is an invariant axis. It's a part of the stable manifold of the equilibrium point of the conducting state. And we have a dissipative dynamical system. If we consider this as a vector field, we take the divergence, it will be negative in the whole phase space. So basically it tells us we can only have fixed points or chaotic dynamics, no quasi-periodic whatsoever. So these are the properties we'd expect our reducer model of this chaotic thermosiphon to exhibit, and we'll see how we can enforce them in the identification process. But first, we need to go from this to just a 3-state variable that would make sense for Lorenz-like dynamics. And so for this, I'm going to use DMD. So you're probably all somehow familiar with DMD. I'm just going to recast it in a more general framework, which is called reduced rank regression, and give you actually the optimal solution of the DMD problem. The one that everybody's using is actually suboptimal. And then we're actually going to use it on our thermosiphon. So who's not familiar at all with DMD? Never heard of DMD? One. All right. Who has used DMD before? Quite a few. Did you use what Peter Schmidt, like the original algorithm by Peter Schmidt, basically? I suppose. All right, never mind. So DMD is basically a system identification technique that was introduced by Peter in 2010 in fluid mechanics, and initially was presented as some kind of generalization of eigenvalue analysis, but for nonlinear systems. But since then, it has been shown to provide actually approximation of the Koopman operator, a fantastic theoretical a mathematical field, way beyond the scope of what we're going to do. If you ask a question, just ask Steve. He's the Koopman guy. And since then, there's been like numerous variants, right? So the idea in a nutshell of DMD is we're going to take a discrete time nonlinear system, xk plus 1 equal f of xk, and the aim of DMD is basically to replace this nonlinear vector value function just by a linear operator. And ideally, we'd like this operator to be low rank so that we can actually construct it. And the idea is, all right, if we can do this, then probably the eigenvalues of A and its eigenvectors can give you some valuable information about like the coherent structure in your system and the characteristic timescale of your dynamics and all this kind of stuff. From a reducer model perspective, additionally, if A is low rank, you can actually replace this whole nonlinear iteration, which scales as n, the number of degrees of freedom you have, by a much smaller system, which scales as s, which is the number of DMD mode you're going to retain in your problem. So that's basically the basic idea. How do we compute this A? Well, we can recast DMD as a reduced rank regression problem where we're going to minimize. So we're going to say x are the state at time k, and y is a big matrix with the state at time, like the one step ahead evolution of the state. And we're going to try to minimize this norm, the norm of this difference over all possible A subject to a rank constraint. And actually, the analytical solution to this problem, it's been known for 70 years. So like the whole DMD stuff, it's actually known like since 1951 precisely. We have theorem to give us what the optimal solution is to this problem. And the idea, I'm not going to do the whole demonstration, it's not very long, but the idea is we're going to start with the unconstrained solution, so we're going to forget about the rank constraint. And this unconstrained solution, that's basically just the least square solution. And so our reduced rank regression problem, we can actually rewrite it as we're going to project our unconstrained solution into a lower dimensional subspace of rank R, where PPH is basically the projector onto this subspace. And after some basic manipulation, we can transform this minimization problem into a trace maximization problem. Where we know trace maximization problem, we basically have to look at the eigenvectors of this matrix here. Right, so we can, it's pretty much, it's really similar to what you would do with CCA, right? PCA, you would not have this CYX, CXY matrix, and this one would just be CXX and not the inverse. And so the optimal DMD problem, a solution, that's basically the eigenvector of the symmetric definite positive matrix. And if X is full rank, these are simply the PCA mode of the output Y matrix. That's just there is to it. If X is not full rank, which sometimes happens, it's the singular vector of this matrix, y Vx, Vxh. That's basically the projection onto the row span of X, which is going to be slightly lower dimensional. But it doesn't really matter. All right, so that's what we're going to do. We're going to use for our dimensional reduction technique. Oh yeah, by the way, once you have P, you can reconstruct Q so that you have the low rank factorization of your matrix. That's the best linear operator you can build given your data. And once you have this low rank factorization, you can easily compute eigenvectors and eigenvalues of this big matrix fairly easily. All right, so we're going to use DMD in our problem. So we have this chaotic thermosiphon, we have the velocity field, we have the temperature field, and we have performed a simulation with where we collected 20,000 snapshots. That's barely enough actually to convert the mean flow, right? Because we have this chaotic system with random switching, actually the 20,000 snapshots are barely enough to compute the mean flow. Anyway, let's do it. So we're going to treat each variable independently, just like Lorentz did, right? Because we suspect Lorentz-like dynamics. Let's do the exact same thing. So for the velocity, we're just going to retain only one mode, exactly like what Lorentz did, and this is what this mode looks like. So it's basically a constant azimuthal velocity. So the sign, the amplitude of this mode will basically somehow give us the flow rate in our loop. And then for the temperature, we're going to retain the first two modes. So this is the first one. So it gives us the left-right anti-symmetry in the temperature fluctuation. And the second mode gives us the up and down anti-symmetry of the temperature fluctuation as well. And I should mention that these particle variables, right, so this is basically a proxy for the flow rate, left-right symmetry, up-right symmetry. There's been some work on these problems. What they've used these exact measurements, so like the temperature difference between here and here, here and here, and the flow rate, to sort of do data assimilation from experimental data of the thermosiphon onto a chaotic Lorentz system. They use precisely, it turns out they use precisely these measurements that DMD is capturing. All right, so that's our projection basis. If we project our 20,000 snapshot onto these vectors, that's what we get. And that's Lorentz. Right? Anyone familiar with Lorentz? That's just the wings. And DMD, even though we just considered like one mode for the velocity, two mode for the temperature, it's a reasonably accurate embedding. Right? We capture approximately 90% of the fluctuation, thermal, and kinetic energy. And quite clearly, this is Lorentz. Right? So our initial assumption that was, all right, it looks like Lorentz. It seems pretty solid. So now the question is, how can I identify the dynamics in this low dimensional space such that I can reproduce and predict the evolution of my system? So for that, we're going to use system identification techniques. Whoa, I'm going super fast. We're going to use system identification technique, and we're going to use SINDy that Steve has introduced briefly before. But first, we have a whole hierarchy of models we could use from that were classified by Wiener in 3 different flavors. So we have black box models. So that's basically we only use input-output data. We don't really care about what's in between. And that's basically what a neural net does, right? You fit it with input data and output, and you try to make it fit the output of your system. Then we have white box models. That's basically what we do in high school. All right, we know exactly, that's basically like first principle equations. We know the model. Maybe we don't know exactly the coefficient, so you've probably all played with like a resistor, like the U equal Ri low for the resistance. Well, you don't know maybe exactly the resistance you have, but you know the form of the model. You have input voltage and intensity, and you try to fit relation between the two. That's really white box model. You know the model is, you just try to infer the parameters. And then we have this gray box region here where you have input-output data, but you also may have like partial knowledge of what the system could be, what the structure could be, or what are like various inductive biases. Like maybe it has some kind of symmetries or invariant quantities it needs to have. And so system identification is precisely in this gray zone because often, at least when we apply it to physical systems, because, well, we've known the laws of physics for like hundreds of years, right? So we do have prior knowledge about what the system should be or what kind of property it should have in terms of symmetries, in terms of invariant quantities, any prior physical knowledge you can have. So we do have, we're in this gray zone. And also that although the exact form of the governing equation may be unknown, right? That's the case we're in. We know it should look like Lorentz, but we're not entirely sure. Because the dynamics, we know they're actually modeled by a PDE in this like infinite dimensional Navier-Stokes space, but it's actually concentrates onto a low dimensional manifold, and we want the dynamics on this manifold for our purposes. So if we consider linear systems, linear system identification, namely in particular for LTI, linear time invariant multiple input, multiple output system, that's a well-established theory. There's like a whole zoo of models and techniques you can use. It's used in a lot of different scientific and industrial fields, from like optimal control, signal processing, image processing, any kind of filters you can use. You can actually recast it as an LTI system. And there's like a lot of different techniques, like the eigenrealization algorithm and for SINDy, which is actually for stochastically driven linear systems. RMAX is one of my personal favorite. And most of them rely on input-output data, so that's basically experimentally accessible data. So you don't have, for linear time invariant system, you don't need to observe the whole system. You really need to observe just a few measurements, and you can reconstruct the whole thing. Either has a state space model, so maybe you only measure U and Y, and you want to reconstruct A, B, and C to get your state space model. The nice thing with LTI system is you can actually use finite impulse response or infinite impulse response. That's basically the convolution kernel that translates into a transfer function, or RMAX process is another way to do. So there's a lot of stuff we can do. For nonlinear system, not so much, right? So if we consider discrete time nonlinear system, like this logistic equation, a nice bifurcation diagram, it's actually closely related to the Mandelbrot set, if you didn't know. The first practical theory dates back to 1887 by Volterra, and that's what we call Volterra Series. So Volterra Series, you should pretty much see it as a Taylor series, but for functions that evolves in time, right, with memory integral. But that was not very practical, and since in the late 80s, actually NORMAX, so nonlinear autoregressive with moving average and exogenous input, has become one of the standard tools you can use for discrete time nonlinear system identification. It's really just a generalization of RMAX, which is a fairly standard linear time invariant model for time series analysis. It's extremely versatile, and one of the nice things is it can actually account for latent variable through this time delay embedding, among other things. The problem is it's actually limited to a discrete time framework, and in physics we have ODEs, right? The language of physics, the natural language of physics, is x dot equal f of x. It's not xk plus 1 equal f of xk. And so transforming from the discrete time system obtained by NORMAX back to an ODE is actually far from being straightforward, and we can really do it just in a few simple cases. So how do we do for continuous time systems? This is actually, I argue it's a harder task than discrete time systems for various reasons, but SINDy seems like a quite promising approach for that. At least it's the one we've been using with Steve for like 5 years now, I'd say. And well, Steve has shown how it works. So you basically build a dictionary of functions, possible nonlinear functions, and then you use sparsity promoting regression to try to find the smallest subset of these atoms from this dictionary that explains your data. Now the thing is this, you can actually apply it not just for dynamical system, but like these idea of dictionary, finding like the smallest subset in the dictionary, you can apply it for any kind of data you have, not just dynamical system actually. So the thing is, this is a combinatorial problem, right? So I'm just gonna write the problem slightly differently than what Steve is doing. So we're gonna minimize the cardinality of our coefficient vectors subject to a data fidelity term here. Combinatorial problem, super intractable. It becomes very rapidly intractable, and so we need to use a convex relaxation of this problem or greedy algorithm to solve this problem. So there's different techniques to for convex relaxation of the L0 norm. So you could use Loiseau, basis implicit denoising, other stuff. All of these they have different like properties. They rely on different assumptions. In the end, they really give you the idea is pretty much the same, right? Some are better than others for noise. Some are better for big data. I mean large models. But in the end, the idea is really the same. Alternatively, you can use greedy algorithm, and that's actually what the hard thresholding sequentially hard thresholding algorithm by Steve is. And the orthogonal matching pursuit that someone was mentioning in the previous talk, that's actually a greedy algorithm to solve this L0 norm penalization problem. My personal favorite is this forward regression orthogonal least squares. It's pretty similar to what Steve was showing, but except that we're going to sequentially increase the terms in the model rather than decrease as is doing. And that's actually, it's my personal favorite because that's what we use in discrete time normax models. Super easy to implement, and we have pretty good understanding of its sparsity promoting properties, and also it has been shown that from a statistical point of view, it's consistent, and it has like all the properties we like for statistical estimators. All right. So as Steve mentioned, SINDy is actually an extremely versatile framework. We can add constraints because it relies, at least convex constraints, right? That's one thing. Not everything is convex. But because we try to minimize a convex function, there's a number of physical constraints that you can either express as linear equality or convex inequalities. And if you can write your physical properties of the system, so that would be, for instance, like what Steve presented, like the skew-symmetric nonlinear term, energy-preserving term in the Navier-Stokes. This convex inequality could be used, for instance, to impose the dissipative structure we've seen for the Lorentz system. It's a convex equation actually in the coefficients, so we can really impose it directly during the identification step of our problem. There's also, we've given some tests. We try to also impose some invariant quantities. So in Hamiltonian systems, so I'm not sure first integral makes sense in English. In French, it's intégrale première. It's like invariant quantities for Hamiltonian systems, trying to bake them into the identification to make sure the system fulfills these physical properties. But that's one thing, but it's not the only thing. You can also extend SINDy for stochastic systems. So this is actually not work from our group, although we're working on it with Jared. So one of the questions is, all right, if I have a stochastic ODE that generates such time series, not really noisy time series, stochastic systems, how can I infer from these time series? What's the drift and diffusion functions are? So this is work in progress. We're trying to improve a bit what's being done in the literature for the moment. It's currently limited to fairly low dimensional system because we need to sample a PDF, and how do you sample a high dimensional PDF? Anyway, last one I like to mention, it's by a group, I guess in Germany. It's called MANDy, and is anyone familiar with TensorTrain formats? Right, quite a few persons. So they basically rewrote the whole SINDy framework using TensorTrain, which allows you In the basic SINDy formulation, for instance, if we consider this library of polynomial functions, its dimension is going to scale like this. So it's going to grow exponentially fast as you increase the number of variables. The whole point is that rapidly you're not going to be able to form explicitly this matrix. If you have 100 state variable and you consider like all the quadratic interactions, you have something like 15,000 terms. Right? So your matrix becomes super large. The idea is for certain classes of functions, polynomial included, actually you can write tensor train decomposition, which is sort of equivalent. We have a few additional terms here than we have here. And you can re-express the whole concept of pseudo-inverse and least squares using these tensor train decompositions that allows you to handle actually high-dimensional systems with SINDy, not just low-dimensional ones. Albeit you need to trade the classical linear algebra we have for tensor train algebras. But that's pretty promising for actually high-dimensional system identification, provided you have sufficient data, obviously. All right, so let's apply all of this to our problem. So these are time series. So that's the evolution of the different DMD modes. So that's the one for the velocity. That's the first mode for the temperature. The second mode for the temperature as well. So these are going to form our training time series. Because we assume, we make the hypothesis that it's Lorenz-like dynamics, we're going to consider a library of functions that includes up to quadratic terms. And the feature selection, we're going to use this for regression orthogonal least squares because it was easier for me to use it. So if we do it, here's the model we get. Right, so in red, you have precisely the terms that appears in Lorentz. And we have a few additional terms that do not appear in Lorentz. But if we simulate the system, so in gray, you have actually the low-dimensional attractor from the high-dimensional DNS data, and in green you have the one generated by this fairly simple system. So it's clearly Lorenz-like dynamics with a few additional terms. And we can easily show, if you do the math, it actually satisfies, because we baked in like the dissipative property, for instance, it actually satisfies all the property we listed in part 1. Yeah?
This is a pretty sparse dictionary. You use just up to quadratic. If you have a larger dictionary, do you also recover sort of the
I tried up to quintic, and I recovered this one.
Okay.
Right. And I actually have, because I have this minus x minus y, xy minus x minus y symmetry, this gives me like super hard constraints on what the functions can be because it has to be odd in x and y. So it reduces dramatically the number of functions I can have by default. If I go up to quintic, I may have a few additional terms, but they really do not improve the quality of the model. They do improve the L2 norm of my error. They do minimize it. But when I simulate it, it doesn't really change qualitatively, even quantitatively, actually, compared to this very simple model.
Does this respect the symmetry or invariance of the original?
Yeah, precisely. Right here, if I replace x and y by minus x and minus y, this equation remains unchanged. So does this one. So does this one. So it does really obeys all the symmetries we suspected it should verify from our Lorentz analysis. One of the questions, anyways, can we further simplify the model? So we have 10 different parameters, but it's like this, negative 92 and positive 93, they look suspiciously similar. So can we actually enforce that they are equal in the identification? That's linear equality in the parameters, convex problem. We can do it, and if we do it, we actually get this even simpler system where, once again, in red, you have exactly Lorentz, and we have only one additional term here. The constant term in the z equation, by the way, is just basically we shifted the origin from the conducting state to the mean flow because that was easier for me to work with the mean-centered variables. So this term doesn't really is not really important. So the only extra term we have computed Lorentz is this one. which we can actually interpret as a coupling between the velocity mode and the up and down temperature difference in our analog thermosiphon. And these are the time series we get. So in gray, that's the time series we get from the high dimensional system projected onto the span of the DMD modes. And in green, it's just this system that we have. And if I were to do some statistical analysis of like the switching time and the residence time on each wings, I have enough time to do like the whole figures, but it's actually a pretty good fit to what we get from the simulation. So what's next? Well, I haven't enough time to go much further than that. As I was saying initially, my end goal, and it's the same as Steve, we want to use these models for control purposes. Right? I want to control the flow. In this case, I want to stabilize the flow in just, say, the clockwise rotation of the convection cell. And so for that, we would need to apply optimal control theory. So far, we've only learned x dot equal f of x, so the uncontrolled dynamics. And what we would actually need is x dot equal f of xu, where u is our control. And that's yet a harder problem, because there's the question of how do you control the system, what kind of actuator you would use to control the system, which is something I didn't do so far. But let's say we do know how to control the system or how to act on the system, then you could actually use SINDy with control, which is like a fairly simple extension of the classical SINDy framework to account for external inputs. And once you have a decent reducer model, and by the way, you could also enforce constraints that this f of xu reduces to this one in the absence of control. And once you have this, you can actually use feedback control to stabilize the system. So this is like a small example using this system with some kind of ad hoc control on the first variable. That's really what we want to have in the end. We want to stabilize it on one wing, but that will be for another time. So I'm going to cut this long story short. So just a few words. So critical dimensional reduction is a critical pre-processing step when you want to apply SINDy to high-dimensional systems, actually. One of the crucial assumptions is actually your high-dimensional system is not that high-dimensional. You have some kind of low-dimensional coherent structure that is hidden. You could use PCA, POD, DMD, time delays, autoencoders, anything you want. But the thing is, at the present time, it's not clear yet which dimensional reduction technique provides the best embedding for system identification, right? Because here, it turns out it works. It also works for the cinder flow. It also works for the cavity flow and a couple of systems we looked at. But really, what we did is we learned the embedding and the system identification separately. So we have no guarantees that the low-dimensional embedding we use will necessarily be a good coordinate system for the identification technique. And there's actually some work by Kathleen where she's combining autoencoders and SINDy all together to try to learn simultaneously the best coordinate transform that gives the simplest dynamical system for our data. For the moment, my personal favorite still is DMD because we have a good understanding of it. And because in big fluid dynamic simulations, we may not have a lot of data in terms of samples in time, right? We may have very high dimensional systems, but we may have just a few hundred or a few thousand samples in time, which may not be enough to properly fit autoencoders, for instance. So I use DMD most of the time because from my experience, it makes the linear term in the system as simple as possible because this is what DMD is designed for. And this is somehow possibly connected to normal form theory in dynamical systems, but this is also, at the best of my knowledge, is actually currently unexplored. We have some ideas, but DMD-like embedding for our system identification purposes actually works better than PCA. If I had done the same thing with PCA, the system would be shit. Right? The embedding would not look like Lorentz at all. Albeit we would capture pretty much the same amount of fluctuation energy. So there's still some work to properly understand which one is the best. Regarding SINDy, so I hope you're now convinced that it's a pretty versatile framework for continuous time system identification. You can really understand, if you're familiar with Normax. Anyone familiar with Normax here? Except for Steve and Jared? All right, so it's basically, if you look at time series analysis, there's this framework which is called RMAX for linear systems. Then there's a generalization which is called Normax for nonlinear system, but still discrete time. So you should really understand SINDy as some kind of like even more general framework for continuous time systems. Super easy to extend for input-output control systems, stochastic system. You can add a limited class of physical constraints. Right? It has to be convex constraints, so linear equality or linear inequalities. But that's still something fairly simple to do, and there's a lot of physical constraint you can express in this form. And something I did not discuss, but Steve emphasized it somehow. Cross-validation is a crucial step to really pinpoint, get exactly the correct model. But finding a good metric is even more important for the cross-validation problem, because for this chaotic system, for instance, if I use just like 1 or 2 times step ahead prediction, which is the one thing everybody does in time series identification problems, I'm going to have a super simple system which is actually linear, and it's going to give me the best 2-step ahead or 3-step ahead prediction error. But if I try to simulate it, it's going to go to a fixed point right away in just 100 time steps. So you need to use like different metric to really identify what's the correct system. What I've used here is actually the autocorrelation function of the signals. Right? So I try to make sure that the autocorrelation function of the DNS data and of the reducer model are as close as possible. You could also use, for instance, compare the probability density functions of the DNS data and the reducer model using, for instance, the Wasserstein norm. Lyapunov exponents are even better candidates for a chaotic system if you can compute them. There's one limitation, however, at the moment with SINDy, we don't really know how to handle properly latent variables. And so latent variables, that's basically variables we do not observe because we don't have measurements to observe them. For discrete time system, you're all familiar with the time delay embedding theorem by Florence-Taquin. That's actually, if you go back to this paper, this actually has nothing to do with time series. It's purely a geometric proof. And so it's well suited for discrete time system. For continuous time system, it's a bit questionable, actually. But there's a generalization which is called differential embedding. So you basically take the function and its derivative and second derivative and third derivative, which is a good candidate because it has the same property as Florence-Taquin's theorem. Although the data should not be too noisy, right? Because you're going to take a derivative of a discretely sampled continuous function. So a few practical tips for SINDy. Basically, what I always do before using SINDy is I try to get physical insight from a similar problem that has already been solved. So that's what we did with Lorentz. And actually, this has proven to be a critical step because until I rederived the whole Lorentz equations, basically the embedding I was using was not the correct one. It was giving me like super shitty results, basically. When you use SINDy, you could start right away with like an overcomplete dictionary. I would strongly argue against it, and I would rather incrementally increase the size of the model up to the point you get a decent one, but no more complex than that. And starting with polynomials is a reasonable idea because at least in fluid mechanics it works in all the test cases we've used. Obviously, for instance, if you use a pendulum, it's not going to work. But basically what you're going to get is the Taylor expansion of the sine theta function that comes in the pendulum. So it's still going to give you some IDs. Looking at the unconstrained least squares solution before doing any kind of sparsity regression is also a good idea because if your least squares solution is shit, it's very likely that your sparse solution is going to be any better. And also, from my experience trying different sparsity promoting technique, not just like lasso or forward regression least squares or hard thresholded least squares, you should really try all of them on your problem because they have different properties, and that will allow you to assess the robustness of your identification. There's some techniques that kind of discard some of the terms, others keep them, get slightly different models. It's not clear which one is the best. So try to use as many sparsity promoting techniques you can to sort of get better ideas of what the model could be, or the family of model that fits your data. And finally, we can add constraints. And once the system has been identified, cross-validate it, cross-validate it, cross-validate it, because I've seen dozens of papers, not necessarily using SINDy, but where they use like super shitty cross-validation metrics. And when you reproduce the stuff, it works for 2 time step ahead prediction. So you have only 2 time step prediction horizon, and then it just doesn't work because they didn't use the correct metric to cross-validate their problem. So thanks for your attention, and I'll be happy to answer any questions.